Hello everyone, I'm Sonia Ruiz Pérez, Product Manager of EFFECTS and RISKCURVES, and I'm thrilled to continue exploring this important topic with you. Today, I would like to welcome you to the second part of our video series, CO2 Hazard Modeling with Effects on Risk Curves for CCUS pipeline transportation. In the previous video, we discussed why it's essential to address the safety of CO2 pipeline transportation in CCUS applications. Today, we will dive deeper into the key safety concerns, starting with carbon dioxide's fundamental properties and how they influence the risks associated with pipeline transportation. Let's start with the properties. CO2 is a colorless and odorless gas that is naturally present in the atmosphere, making up about 0.04% of the Earth's atmosphere. It is a byproduct of processes like respiration, combustion, and other natural and industrial processes. Depending on pressure and temperature, CO2 can exist in 4 different physical states. First, we have gas at normal atmospheric pressure and temperature, liquid under high pressure, as a supercritical fluid at pressures above 74 bar and temperatures above 31 degrees Celsius, where it behaves as both gas and liquid. Finally, CO2 can also exist as a solid at very low temperatures, forming what we commonly know as dry ice. What makes CO2 unique and also potentially hazardous is its density. It is 1.5 times heavier than air when released in its liquefied or supercritical form. This means CO2 behaves as a heavy gas, spreading close to the ground and accumulating in low-lying areas or confined spaces. This behavior poses significant risks in both open areas, where large releases can form extensive clouds, and enclosed or poorly ventilated environments where accumulation can quickly reach hazardous toxic concentrations. In addition to its density, CO2 has some other characteristics that create safety concerns. When dissolved in water, CO2 forms carbonic acid, which can corrode pipelines, valves, and other industrial equipment, increasing the risk of leaks and structural failure over time. While CO2 is non-flammable and often used in fire extinguishers, its classification as non-toxic can be misleading. At high concentrations, CO2 displaces oxygen, creating an asphyxiation hazard with symptoms such as dizziness, unconsciousness, and in extreme cases, death. Now let's focus on pipeline-specific hazards. Pipelines transporting CO2 are typically designed to handle this chemical in its dense phase, either as a pressurized liquefied gas or a supercritical fluid, at pressures exceeding 100 bar. While this compression improves transportation efficiency, it also introduces unique hazards. First, pipelines transporting highly pressurized CO2 pose a risk to infrastructure due to the potential for ruptures. That is because a rupture can cause a rapid release of pressurized CO2. For buried pipelines, on the other hand, the escaping two-phase flow can displace soil, creating a crater. This soil displacement may expose nearby pipelines to structural damage, increasing the risk of domino effect with cascading failures. CO2 can also pose health hazards. For instance, when CO2 is released, this rapid expansion of dense phase CO2 causes it to cool into a mix of gas with solid dry ice, creating a cold vapor cloud. Exposure to this cloud can lead to frostbite, cold burns, or even lung damage if inhaled. Prolonged exposure to CO2 concentrations above 0.5% in volume, which is the OSHA permissible exposure limit, can result in symptoms such as headaches, dizziness, and nausea. At concentrations around 4% in volume, CO2 becomes immediately dangerous to life and health, which is a concentration typically known as IDLH concentration. CO2 can also present environmental hazards, as CO2 leaks can undermine the environmental benefits of CCUS by introducing risks to ecosystems. High concentrations of CO2 can displace oxygen, creating asphyxiation risks for wildlife. It can dissolve in water, forming carbonic acid, which can contaminate aquatic ecosystems, and absorb into soil, harming vegetation and disrupting local ecosystems. Managing these risks is critical for the safe implementation of CCUS technology. Understanding these hazards is the first step in mitigating them and ensuring the safety of people, assets, and the environment. One of the most effective ways to address and reduce these hazards is through hazard modeling. By simulating different release scenarios, we can predict how CO2 behaves under various conditions and assess the associated risks. In our next video, I will introduce you to the challenges of modeling CO2 hazards. For now, thank you very much for watching, and I'll see you in the next video.